Sir,
Hi, hello.
sir, could you please discuss week for assignment questions, sir? I'm not comfortable with the cascading type questions, sir. From question six onwards.
Week 4.
Week four, sir.
Yes, yes. I think they these time week after question number 5 I had missed in last session. So
Yes, sir.
in this session I will discuss a few questions from week 4 actually, and this is the one, right?
Yes, sir. Yes, sir.
I will discuss this question first. Let's wait for a few minutes.
Oh, sir,
Okay.
afterwards, could you please discuss that current source also, sir? 2 week. Assignment is getting closer, no, sir. After
Uh,
the upcoming week, if you discuss also, that won't be that much useful, sir.
what do you want me to discuss?
Current week content also, sir. That current sources, current mirror topic as well. If you believe
Okay,
that
in
you,
this in this presentation, I have not kept those questions, but yeah, I can discuss generally with you. No problem.
yes, sir. Thank you, sir.
Do you have any other questions till 6:05? We can discuss general things if you want to say anything. We
Okay,
have
sir.
time till 6:05. If you want to say anything, you can.
Yes, sir. Sure, sir. Sir, in from week one iteration method, we will find out that we assume the voltage, no, sir. Week
Mm-hmm.
one.
Mm-hmm.
Through iteration, we will find out that drop voltage. There, I am
Mm-hmm.
not at that week. I didn't get the point, sir. I missed the question only.
Okay, so what exactly do you want? Wait a
Week
second.
question one only, sir.
Mm-hmm. So now you can tell me.
Sir, week one question one is there, no, sir.
Mm-hmm.
There would be a diode in series with a resistor there that voltage drop won't be given through iterative method. We'll assume and we'll find out through
Yes.
series connection.
Mm-hmm.
Yes, sir. There I don't know where I lack. I need to know. I need to get somewhat clarity on these questions.
Okay, let me just check if there is week 1 here. Have you watched the sessions on YouTube?
Yes, sir. Sir, I am going through your recording sessions in YouTube sessions, sir. Recently, last week also I completed, sir.
Mhm.
1 hour 39 minutes duration.
Mhm. Okay. And the next, and there is one more TA that also goes
Yes,
session.
yes, sir. Yesterday session also I attended, sir.
Okay. So is this the one you're talking about?
Yes, sir. Yes, sir.
Okay.
No, and before the question, sir, I think.
Mm, this one? This one,
Yes,
right?
sir. Yes, sir. This one.
Okay, so what have we done here? Mm, okay, so we in this type of questions, what you need to do is you need to assume first some voltage drop, right? So here,
Yes,
let's
sir.
say, 1 second. Here, let's say this is VD. So you assume, you must have seen in the questions that VD is near about 0.65, right? So this is a
Yes, sir.
standard, the standard potential, yeah, cut-in voltage for diodes.
Silicon.
Yeah, silicon diodes. So you go on with this as hello.
वकील कहाँ बा वकील कहाँ बा
1 second.
पढ़ा तो तनिका लिखी
Okay, so first step is you assume this VD equivalent to 0.65. Okay, then you perform this KVL, right? KVL, you know the KVL from this node V0 to
Yes,
0,
sir.
okay? Then you perform this KVL here. I have written this KVL here.
Yes, sir.
You will get some current, right?
Yes, sir.
Okay. Once you get
We,
this, mhm.
their current should be same, sir. We'll substitute the values same to the diode current equation also. We'll check it
Okay,
they are
yeah,
matching or not.
yes, yes. So after this, you will get some current value. Then again, you have to go on repeating it, right? Or what you can do is you assumed VD, right? You assumed VD. You can substitute in this equation. You will get some ID, right?
Yes, sir.
Then from this equation, you can calculate VD. There are two ways. Okay, so from this equation you can calculate VD. Then you substitute back this VD in this equation. You can go on. There is a one thing why you need to know when you should stop, right?
Yes, sir. There I am commit a mistake, sir.
Hmm. So what you do in if you
तो हम जाने
so
Sir, I stopped
stop.
from 1.77, sir.
Okay, so you need to stop somewhere, right?
Yes, sir.
So let's
Actually,
suppose, okay, let's suppose you assume first 0.65 VD, then after first iteration you got let's say zero point 0.6, okay, then in next let's say VD naught, VD1, VD2, in next iteration you got 0.63, VD3. Now your solution is converging somewhere, VD4, 0.6351. So you can see the difference as you go on iterating, your difference goes on decreasing, right? So you can keep on condition. Let's say the difference is let's say less than 1 milli, stop. This is how you okay
yes,
okay.
sir. But at the time I stopped from 1.177, sir.
Mm-hmm.
I mean, after the question answer is 1.80. There I commit a mistake, sir. Could you please solve it, sir? I mean, I may get more clarity, sir. I
Maybe
mean,
we may have solved it. No,
in
here
new paper, it would be more clarity for me, sir.
okay
That
here
is the only question.
here
Yes.
if we have solved it. Here we assume first here you can see here from equation B, this is V naught minus VD.
Yes, sir.
Okay, you are getting the wrong answer.
Yes, sir. For that
This
question only I get
this
wrong answer.
this question is actually options are not correct. Here you can see I may have told in the session also.
Okay.
Here VD1 maybe I may have written somewhere. Okay. I remember now. This options, the four options that were given in this question are not correct actually. So
Okay.
I may have said to you earlier in the previous session as well. You must have forgotten. So the options actually for this question one are not correct. So that's why you must have misunderstood your confidence.
Okay.
So so that it's a simple method. Like these are equation A, equation B, right? You substitute some VD. Okay. You substitute the VD in this equation for ID, right?
Yes, sir.
You will get some ID here. Okay. Then substitute this ID in this equation.
Okay. We need to
You
get
will
a similar VD. Yes.
you will get some VD. Then again you substitute it back in ID. Then you again calculate ID and substitute it back in VD. These are the steps. You should get an answer around 3-4 iterations. Okay.
Okay.
So the options given in this question number one were not actually correct. So, like for example, VD1, I am getting 0.7814. I think you also had the same answer. Last time, I guess you told me. Mm, hello, hello.
Yes, sir.
Your voice is
Yes,
not
sir.
audible. Are you speaking something?
No, sir. No, sir.
Okay.
Could you start the class, sir, afterwards? Sir? I mean, somewhere waiting. Without waiting.
So do you want anything else?
Nothing, sir. Afterwards, I will ask after class.
Okay. So let's go to week. No. Okay. So this is actually these questions are from the past week. We'll see how we can solve these questions. Let's just first write the details. This is for transistor 1. GA1 is 1.6 millisiemens. And for transistor 2, GM2 is 1.8 millisiemens. Okay. Similarly, for this transistor, GMB1 is given to us as 0.32 millisiemens and GMB2 is zero point 0.6 millisiemens. Also, there is a channel length modulation, so RDS1 and RDS2 are given. RDS1 is 20.63 kilo ohms and RDS2 is 23.89. 20.89 kilo ohms. Okay, so this is the detail. What we need to do is we need to find V output by V in. Okay, so what will be our step? Okay, so what will be our first step? We need to find V output by V input. That is small signal analysis, right?
Yes, sir.
So equivalent circuit. Let's solve this equation. Let's solve the circuit by using equivalent circuit. Okay, so we can get a small signal gain. That is V output by V input. Okay, let's just draw it. I will draw the circuit. If you are confused with some connections, do let me know. And one more thing first, before we draw the circuit, we should know that both of these devices are NMOS, right? So if I note down these, this is drain, this is source, this is drain, this is source, and this is gate. Okay. So first, let me just draw again here. This will be for small signal. This will be grounded, this will be grounded. We need to take V output from this node. Can you draw on your own paper with me? Try to draw it
Yes.
on your own as well. I will just wait for you guys. If you can draw, then you will let me know when to start. Let me just draw for the first circuit. This is in. Okay, let me know what are the other connections. This is my source. Draw on your paper, then take your time and then let me know. This is for M1. Now I need to connect it to M2. When you are done, please turn on your mic and dictate me the connections.
Yes, sir.
Mhm.
Sir, to source terminal resistor is connected.
To the source terminal, right?
Yes, sir.
Okay.
And another MOSFET, VN is not present, VN is 0. So we will take care of GM1. Okay.
Okay, let's say
Then
this is
RTS1.
grounded. This is
Yes.
grounded,
Yes.
and this is a source. This is also grounded.
Yes. One more resistor will be present. That is RDS1.
Okay, let me just first draw it. This is GM2 VGS 2, and this is
GMP.
GMB2 VBS. Okay, 2, and we have
One
this
resistor.
resistor, right?
RDS2. Yes.
Okay, so everyone is
Because
comfortable with it?
yes, sir. VGS2 is 0, no, sir.
Yeah. I will
So
just cancel these out. So to understand, I won't directly draw the final circuit because some may not be able to understand what happened. So here for this circuit, this is M2. As you can see, this is my VG, this is my VS. VG minus VS for M2 is 0, right? Both are grounded. So GM2, VGS2 will be 0, and GMB2, VBS2 will be 0, right? So what remains is RDS2. So RDS2 comes, oh, one second.
in series with resistors.
So RDS2 is in, so this implies RDS2 series with R, right? Okay, let's just draw the circuit again. So this is my R plus RDS2. This is GM1. Let me just only write GM1 and GM2 here. Don't confuse it. It's not GM, it's GM1 multiplied by VGS. GMD1. This is RDS1. Okay. So now we need to find V output by V input. Now it seems easy, right? So let's say this is a current of I output. So can you directly tell me what will be the current flowing through this R? If you can look here, this is node 1, this is node here. What will be current flowing through this?
GM1 plus GMB2.
GM1 plus GMB2? Why is GMB2?
So this current source is there, sir. This current will be get added at this node, sir.
So it is GMB1, not B2, right?
BM1, sir. BM1.
Okay, and so let me just note down this as this is a node S. So KCL at S. So what you are telling me is the current through R plus RDS2 is GM1 VGS plus GMB1 VBS.
VPS.
Is there something more?
Yes, sir. Through RDS1 also we needed to find current, right?
So what is that? Can you tell me what is that current?
It should be subtraction of these two currents, sir.
So here this node is at potential V out. This node is at potential V S.
Yes, yes.
So there is. Can you? I will just answer this. Can you turn off your mic? There is a noise coming from your mic. Okay. So this is a resistor, and this node is at V output. This node is at S. So this is your RDS1. So what will be the current? Simply, right? V output minus Vs by RDS1. That is your Ohm's law, right? So there will be one more current component that is equivalent to V output minus RDS1 by Sorry, not RDS. So this is one thing, but can you directly see from this figure, I output is coming in this node. If I just draw two nodes, here is I out. So what will be the current here? You can turn on your mic, you can just directly tell me. These are two nodes connected to the end. What will be the current? I out directly, right? So similarly here, the current is coming to this node and now they are living from this node. There is no other component, right, where the current can flow. So you can have directly told me that the current here is also I out, right? So this is equivalent to I out. Is it clear?
Sir, could you please repeat again, sir?
So I told you that if a current comes to a node here, like here, and there are set of elements here, n number of elements here, but they have a common node here, okay? And this is a final node. So there may be multiple elements where the current can flow, but they finally reach to this node here. So whatever is coming in has to leave also. So let me just write.
Yes, sir. Kirchhoff's current law. Yes, sir.
Yeah, whatever comes in
Incoming current is equal to
has to leave. Okay, so my input current to this node has to be the output current at this node. So that is equivalent. Okay, so I output here comes here, so here should be also I out. So this is one thing. Now let's note down this, write it as an D node. We can just directly write now KCL at D. So KCL at D is simply I output is coming in and these currents are going out. Let me just write it. If you are not able to follow, please let me know. And this will be V output minus Vs by RDS1 plus GMB1 VBS plus GM1 VGS. Okay, and now Vs. Can you tell me what is Vs? Vs is this potential. Is it? Your voice is breaking. Your voice is breaking.
Sir, Vs is I out into R plus RDS2, sir.
Okay, so Vs is I out R plus RDS 2,
Yes,
right? Correct?
yes.
Okay. This is all right. Now we can write it as V output minus I output R plus RDS2 whole divided by RDS1 plus GMB1. This is VB. VB is 0. Let me just first in this step write it VB minus Vs. VB minus Vs, then we have plus Vg minus Vs. Okay, this is it. So my Vg is here. What is Vg here? Vg is V in, right? Vg is V in and Vs is I output times R plus RDS2. Now we can write it in terms of I output and V out. So my I output is Sorry. So I output is the output by RDS1 minus I output R plus RDS2 divided by RDS1 plus GMB1 Vin minus GMB1 Vs again, that is I output times R plus RDS2 plus GM1 Vin minus GM1 I output R plus RDS2. Okay. So I will just transfer the I out terms on the LHS. So it will be I output, take it as in common. This will be 1 plus GMB1 R plus RDS2, this term, and I have this term and this term, plus GM1 R plus RDS2 plus R plus RDS2 by RDS1. So this comes out to be equivalent to,
Sir, sir, 1 minute, sir.
okay,
Sir, before the equation, V out minus first two equations I understand, sir.
mm-hmm.
I out, okay, GM, VGS, VB minus VS, sir. GMB,
VB mine, okay,
yes, sir.
this one.
Afterwards, yes, sir. This one, GMB, yes, sir. Yes, sir.
So this is just here edit term, this term.
Yes, sir. That one.
One second. So what is the confusion?
Means actually VB source is we find out no sir. So, source.
Yeah, I have just written this in next step here.
Oh yes, sir. It's fine.
Okay, okay. One second. Okay. Since I don't need to do it in.
Sir, slide is not updating, sir.
Hmm?
Slide is not updating. What and all you are writing?
No, I have not written anything yet. So wait a second. I was just checking here. I don't need to write actually. I output here. So it should be. I will just keep it as an 0. Hmm. From this onwards, since we are doing the analysis from this point, so it will be directly at A. One second. Hmm. Okay. So where were we? So this is the output by RDS1 plus GMB1 plus GM1 the input. Okay, and this is, let me just note down this whole term as alpha. So this is alpha. Now one more thing. To get an answer, we need to have it drawn somewhere else. No. Here, at this node, let's write a KCL at this node as well. That would be a simpler one. Simple, as you said earlier, that will be simply equivalent to GM1 VGS plus let me just filter the circuit. Okay. Have I written it correctly here? Have I made the circuit correct here? Hmm. This is yes. Output and input. Okay. Let's first write I out. We had written I out to somewhere. Here, right? This is the output. Oh, I've done a mistake here. Actually, you didn't correct me as well. Yeah, we here is not a V output. V output has to be taken from here from this node. That's why there was a complicated relation. So this is actually V output. We need to rewrite the equations. Let me just keep it as it is. So which type of amplifier is this?
Source degenerative amplifiers.
Hmm? Common
Source
drain.
degenerative.
Oh, that is another thing when you connect to the source. But this is a type of amplifier. We have common source, common drain, common gate, right?
Yes.
This was a common drain amplifier. We had to take output from source. So we did a mistake. So that's why the analysis was that complex. So let's just redraw the circuit. So this is our V input. This is our R plus RDS2. But this time this will be output. Okay. I can go quickly. GMD1. This is RDS2. RDS1, sorry. Now this is ground. We need to calculate V output by V input, right? So if I directly denote this as a node, so if I write KCL at A, so that will be simply the current coming in to the current going out. Current coming in is GM1 VGS plus GMB1 UBS plus here at this node this is ground, at this node this is V out, so this will be 0 minus V output by VD RDS 1, and that will be equivalent to current going in this branch, that is V output divided by R plus RDS2. Okay, So now this is GV1. I will directly write this as VGS, that is VG minus VS, that will be V in minus GM minus VS. VS is here. What is VS here?
V out by
VS is V out, right?
yes,
VS is V out. So this will be simply B is 0, so GMB1 will be V out minus V out by RDS1 is equivalent to V output divided by R plus
sir. What about VB,
RDS2.
sir?
VB is a body bias that's kept at 0.
Oh, yes.
Okay.
Sir, whenever VB is given, we need to take care of other one also, sir.
Yeah, you should keep it as 0 unless it's given. Okay.
Yes.
So we have is, let's take V output as common. So this will be GM1 V in minus V out. So this will be GM1 plus GMB1 plus 1 by RDS1, and that's equivalent to V output by R plus RDS2. If I just, this is a simple math now, so this will be GMV1 V in is equivalent to V output. So this will be GM1 plus GMB1 plus 1 by RDS1 plus 1 by R plus RDS2. So we need to find V output by V input. Denote this term as alpha. So this will be V output by V input is simply GM1 by alpha. Now to check whether this is correct or not, correct equation at least, so what we do? Dimensions, right? Units. So can you check, are the units correct? Siemens, 1 by R is?
Siemens, sir.
Oh, so it's correct, right? So this also is Siemens, and this one? This is
Siemens.
1 by R plus RDS2.
Yes, sir. Resistance plus.
So this is also Siemens. So this is correct, right?
Yes, sir.
So this is Siemens into voltage, so it is correct. So this is one way to check. If you have, for example, this helps in checking the units, this helps in solving the MCQs as well. So there may be some, let's say, equation, which of the equation is correct. Okay, so you can check the units also. That is one way to cross-check with the options directly. Okay, so this is for now, this is what we have got here. So if we just calculate alpha is GM1. So can you tell me the value? So have you written somewhere? Please wait. No?
Yes, sir.
So can you tell me what is GM1?
1.6, sir.
1.6 milli.
No, sir. 1 millisiemens.
So GM1 is 1 millisiemens.
Yes, sir. GM to 1.1.
One second. GM1, you are not talking about the values which I have here.
Assignment questions, sir. Values I'm saying.
Okay, there are different values. Here the GM1 is 1.6. Can you note down? GM1 is 1.6.
Yes, sir. 1.6, 1.8.
1.8. GMB1 is 0.32.
1.6, sir.
And 0.6. RDS1, RDS2 is 20.63 and 23.89.
Yes, sir.
So this is 1.6 milli, and GMB1 was 0.32
Yes, sir.
plus 1 by RDS1. RDS1 was
20.63, sir.
kilo,
Yes, sir.
and this is R plus RDS2. R is
RDS2 is 23.8, sir.
R is 4.6 kilo ohms.
Yes, sir.
Plus RDS2 is 23.8.
Yes, sir. 20.8. 28.2.
Hmm?
Addition, it would be 28.2, sir. Addition.
23.8. Okay, okay, you are talking about addition. So this will give me alpha as, let me just pick up the calculator. This is 1.6 plus 0.32 plus 1 divided by 20.63 plus 1 divided by 4.6 plus 23.89. This comes out to be 2.0035 milli. Okay, for the same value. Now V output by V input will be GM1. GM1 is 1.6 milli divided by 2.0035 milli. Milli will go
0.79, sir.
0.79.
86.
Okay, so this is the answer for this question. So what was the difficulty you were facing in this question? You just told me before starting the session.
Yes, sir. Now it's clear. Now it's clear.
Okay, now it's clear.
Yes.
Okay, so this was one approach. Another approach would be, we had discussed in the last session, anybody knows?
I just need a small clarification on this.
Okay, please, yeah.
So yes, so I just wanted to know the body substrate, sorry, BS, body and source potential for both the MOSFETs.
Okay, so here mostly you want to know the physically how that is connected, or what has to be considered in these questions.
Yes, please. How is that connected, and how does it like affect the choice of VBS in both of these transistors?
Okay, so for the question point of view, here you have to treat it as 0 because it's not given, right? So usually,
Okay.
so let's say this is actually like this. You know MOSFET, right? So this is your source N plus, this is your drain N plus, and this is your P well, right? So what you do is you connect a body terminal as well, that is also P plus, right? So here if you can see P plus N plus, they form a diode, right? You don't want your diode to be conducting when MOSFET is operating, right? Right? So here you connect the source terminal, you connect to the body terminal, and this is your drain terminal. So VBS is across the diode now. So what you want is either VBS should be negative, or in most of the cases these two are shorted, so these most of the time stay at 0. But here if they are not connected, let's say VB and VS are not shorted, if not shorted, okay, so they should be negative, right? So you don't need to give a voltage at VB. So if you don't give a VB voltage, so that is VB minus VS, so that will be 0 minus VS, that will be minus VS. So that will be inherently at negative potential. So a negative potential means but this should actually VSB. Yes. Sorry, not VSB, VSB. 1 second. This is NMOS, this is P well, this is N. VBS. Yes, correct, actually. VBS. At VBS is equal to negative, that means the diode is reverse biased, right? Is it correct?
Yes, got it.
So,
So for
yes.
so with respect to this particular problem for M1,
Hmm.
so we didn't consider. So there is so in this case the VB is 0 and it's not basically shorted to the source terminal. That is what you mean. That
So,
is why.
yes, if that was shorted, that would have made VBS equal to 0. So
So
there won't be any this component there.
okay, okay, okay.
Mhm.
Yes, got it, got it, got it.
Okay.
Thank you so much.
So another approach, like we discussed in the last session, does anyone remember what was the two step? What were the two steps?
Intrinsic gains.
One was to first calculate output or
Output,
output
output
impedance.
resistance.
Yes. And
Conductance.
short circuit transconductance, right? This was one of the methods. So what we will do in this part, you have to calculate the impedance at source node, right? So this is, this is RDS, sorry, not RDS. This is R plus RDS2. So now you will connect here some Vx, Ix to calculate. For the limited paper, I will just write here RDS1. You ground this node. Okay. So what you need to do is to calculate R out, you need to find Vx by Ix. Can you do it?
Yes.
You know the procedure, right? You have to just use the KCL at this node. Find Ix in terms of Vx, then find this relation. This will give you resistance. So one is this, and then after that you will have to find the GM. In GM, what you need to do is you need to short. V output should be grounded and find.
Sir, I am able to find the resistance, sir. Could you please tell me about how to find the
What
transconductor?
what?
R out, sir. R out I find out, sir.
Mm-hmm.
It would be R plus RTS2 in parallel with
Yes,
RTS1.
yes. Yeah, that will be R total. R total will be R out parallel to R plus RDS2.
Yes, sir.
Yeah, right.
My
So
question is how to find out the transconductors. Could you please tell me? Yes.
here you have to find I out V in. Okay, you want me to find it? Okay. So that
Transconductors.
okay. So as I said, we have one paper here. Let's draw the circuit here. This is grounded. V in has to be not grounded this time. Sorry. You can correct me along the way whenever you find me having some mistake here. Okay. So this is V in. Again, we don't need. We want to find GM, right? You understood the R out part. So we only need to find RDS.
Yes, sir.
GM.
Yes, sir.
Okay.
Yes.
1 second. So this is RDS2. So GM, for GM we need to find I output by V in. Right? So I output is flowing through this branch. This is GM VGS. This is GMV VBS. Plus this is RDS1. It's correct till now? Second. So now if you write KCL here, so that will be, I output will be GM1 VGS plus GMB1 VBS plus here this is grounded here.
0 minus
One more thing, we know that when you have to calculate GM, that is V output should be grounded, right?
yes sir.
So there here this is grounded here. Okay, so just remember that. Okay, so this will be,
Sir, VOT is grounded, then the R plus
okay, that will be 0 minus, hi, this is short, this will be shorted, this is shorted, and from this node to this node, this will be simply 0 by 0 minus 0, there is no current will be flowing, so this is equivalent to I out, so I out will be simply GMV in minus GMVS plus
minus GM B1 VS.
Yeah, sorry, minus. But do you notice one thing, that Vs is also 0? So this will be 0, this will be 0. Is it understood? Vs is 0?
Yes sir.
Okay, so this will be simply GM1 V in. So my effective GM is again
GM. Yes.
GM1. Okay? Understood?
Yes sir. Yes sir.
1 second.
Fine.
Okay. So this is clear. So now you're done with this. Okay, so let's just do one thing. Let's do this. I have written it somewhere. Let me just show that to you guys. Okay. So now, if you want to know, if you want to remember some few things here. What is the gain for the circuit?
Sir, minus GM into sir GM into R naught.
Okay, let's. This is
RD.
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 So this will be RD parallel
RL.
RDS.
RDS. RD.
Okay. So you know the steps. Simple. V in. This is ground. GM VGS. This is RDS. You know how to solve this, right? So next is, if you want to increase gain, okay, you want to increase gain. So what comes to your mind? What we will do?
Either we need to increase the
GM.
sir, or
Okay.
resistance sir.
Let's say GM is fixed. GM you cannot tinker this value. GM is not in your hand because GM. What is GM? What is the value for GM? This is mu H Cox
Cox W by L
W by
VGS.
L VGS minus VT. So VT is a material property, right?
Yes.
That will depend on the doping and all. Okay. So again, mu n, it's a material property.
Yes.
Cox is epsilon ox bit Tox. So that will depend upon your oxide thickness. Let's say you cannot change this while doing the circuits, right?
They are process parameters. Sir.
Yeah, right. So W by L, you cannot change these during your analysis. So what you can do? You want to increase gain. So you cannot change this. So there is this factor. You want to increase this.
You decrease the value of RD.
No. If you decrease the value of RD, these are in parallel, so it will take the lowest value, so the gain will decrease. So you want to increase actually the load. Okay. So now the thing is, you cannot connect. You will say that because RDS is always there's an intrinsic gain, maximum gain you can get is GM RDS. RDS is greater than usually greater than this resistance. So if this is connected in parallel, so this will be almost equivalent to RD because this is usually low. So you cannot connect a very high resistor in series, right? So there are another ways. So do you know anything? Wait a second.
Yes, sir. While cascading will increase the gain, sir.
Right, you're right. Okay, let's just first see one more thing before we go to that step. So what is the R out here? Looking here. Can you calculate? Can you tell me the answer? What is the R out here? I want you guys to know do this now because it was easy. Calculate R out. Looking into the source. I will wait for your answer.
Sir, Ix is
Mhm.
equal to Gm. Uh, uh,
What is
yeah,
R equal to?
sir. 1 minute, sir. Ix plus Gm VGS. I'm writing
So
KCL.
give me the final answer. What is the R out here? Looking into the source. Resistance. You have to calculate the resistance. Anybody else, if you are done, can answer.
Just a minute, sir. I will say, sir.
So the GM, I mean the overall conductance in this case would be GM plus 1 by RDS. So the output resistance should be inverse of this.
Mm-hmm.
Um, so 1 upon
One.
GM plus 1 by RDS.
1 second. 1 second. So you got this what 1 upon
Uh, GM
mhm,
plus 1 by RDS in the denominator. Yes,
1 by RDS.
yes, please.
Everyone got the same answer. Check at your end. Everyone is able to do it.
Sir, yes, sir. Sir, my question is, in the same manner I only did, sir. What mistake I did, sir? Sir, here, while testing this input voltage, also we will ground it now, sir.
Mm-hmm.
Input voltage and output voltage both should be grounded, and we need to
Yes,
take.
yes, yeah, yeah. Yeah. Whenever you want to calculate the impedance, you short and ground the other sources. Okay, just do this. Continue doing. Don't stop. Just remember that you need try to remember these values. Like for example, looking into the source, the impedance is 1 by GM. Okay. Now, similarly, if I calculate looking into the drain, what is the looking into the drain? So this is looking at the source. That comes out to be, if there is no resistor connector, that will come out to be equivalent to RDS, let's say. So just try to remember these values. This will help you in,
Sir, while looking at to the drain, it would be RDS, sir.
yeah, yeah. So calculate, you first calculate the what is looking into the source. Are you able to do it or not?
Yes, sir. Now I am able to do, sir.
Anyone else has any confusion in this? If no, then we just found out that if we look in the source, the resistance comes out to be 1 by GM. That is actually pretty high. Okay. Now looking into the drain, you know that is RDS. Now if you want to increase the gain, we have two ways. One is diode connected load. It's called as diode connected load, and another is current source. Okay. Mhm. So now I will give you this one. This is, can you tell me what will be the resistance here? In this case,
1 by GM, sir.
or in this diode connected as well, this has a load connected.
Yes. Diode corrected means MOSFET will be in a saturation, sir.
Hmm. So this is all also equivalent to,
Diode, sir.
and if I connect it now with, so now this is also a very high, right? Now if I connect it to some transistor, my gain will be, if this is 2, this is 1, so this is 1, this will be GM1
into GM2.
into
GM2.
1 by GM2, right? Because this is the resistance. Here you write GM multiplied by R out is your gain, right? So here R out is our GM2, 1 by GM2. Okay, so this is 1, another is, and one more is, was it understood?
One more PMOS is connected, sir, to the box.
So this was understood, right?
Yes, sir. Yes, sir. Through that relation we said, no, sir. GM into R naught. R naught will find out as 1 by GM.
Okay, so another is now if we connect like this, so what will be the gain here? Can you tell me? First calculate R out here. This has GM, so gain will be, I will just writing the magnitude, so that will be GM multiplied by R out. R out. Now, can you tell me what will be R out here in this case?
R out should be RDS2, sir.
This is PMOS, right?
Yes, sir. We need to find first bias voltage to be in a saturation.
Okay. So let's assume the device is in saturation because then only we can use it a current source. You know the current source. What is current source?
Yes, it has infinite resistance, sir.
Right. Absolutely. And voltage source?
0, sir.
Ideally, right? So,
Yes, sir.
so when you see the MOSFET characteristics, these are MOSFET characteristics, right? So when you tell your, when you say that MOSFET,
Saturation.
MOSFET as a current source,
VDS should be greater than VGS minus VT, sir.
right? So that means actually this region
Yes, sir.
where the current is constant. So this will be my current source at particular VGS. This region cannot act as a current source. Okay. So MOSFET is a current source. That means no matter how much VDS you change, the current remains constant. Similarly, voltage source, it will behave like this. Not D, just random, any current. Sorry. Let's say if IV for the voltage source is like this, let's say for a diode acts as a voltage source. So no matter what voltage there is a constant voltage drop. No matter what voltage you increase, there will be a fixed voltage across this device that we call as a cut-in voltage, right? That you must have used during your diode questions. So now you know the R out is simply here. This is its drain, this is its source, and R out would be simply RDS2. So my gain would be GM1 multiplied by RDS2. Okay, so this RDS2 is usually very greater than 1 by GM2. So that means that from the previous case, the resistance was 1 by GM2, and in this case, the resistance is RDS2. So gain is higher in this part when you use it as a current source. So if we summarize this, what we have done, if we summarize this, so we have three cases. We have simple RD, and gain is
GM1
G
into RFD, sir.
RD parallel
R,
RDS.
RD.
Okay, and if I have 1 second, another is connecting as a current source. Mistake, actually this is correct. These are the three cases, and you will see that this has the maximum gain. So this is one way to increase the gain in the circuit. Now another important thing before we go to next part is we need to remember one more thing. You just remember these three. What is the gain? And another is if we have source Degeneration. What do you know? What do you mean by source degeneration? What do we do that in that case?
The source is not grounded, sir. Instead of source grounded, there would be a resistance.
Hmm.
There would be a drop across the source also.
Okay, so if I just draw the circuit, can you calculate R out? And this R out, you need to remember. This is a good value, good equation to remember because it will help you in solving the questions. So can you just let me know what R out will be?
Sir, R out at the drain side or source side, sir?
Drain side. R out means where you are taking V out, right? So just calculate
Yes,
this
sir.
R out. Do this, let me know what you will find.
Sir,
Mm-hmm.
sir, through small signal analysis, we can find it now.
So
As
can you
they,
tell what is the value?
uh,
Is it RD parallel RS plus RD parallel RDS1 plus RS?
Mm, okay, no, it's not like that actually. Let me just draw.
sir, RD plus RDS3, 1 plus RD into RDS3, sir.
RDS3. I have taken RDS3. There is only one
Sorry,
transistor.
sorry, RD, sir, RDS, sorry.
So what is R out? Step by step. R out is.
Drain resistance RD, sir,
Mm-hmm.
plus source resistance RS, sir,
Mm-hmm.
parallel with RDS3, sir.
Parallel RDS. Okay.
Uh,
This is
divided by uh, 1
whole
plus,
divided by whole or
yes, sir.
on
Whole, sir.
here
1 plus RD
1 plus RD.
into RS parallel with RDS. Yes.
Is this multiply here in the numerator or is addition here in the numerator as well?
Numerator addition, sir. Denominator
Is
product,
it
sir.
is it how what you got?
Yes, that product.
Let's see if this is correct. Okay.
Yes, sir.
So what we will do is we will connect here VX IX Okay, let's see what we will get. Okay, my R out is here Vx by Ix, and my R total will be R out parallel to RD, right? So let's see what I will get, and then we will compare the two. Okay, so here Ix will be equivalent to Vx minus Vs by Rds plus Gm Vgs, right? And here, if you can see, Vs is simply Ix times Rs. Is this correct? I hope it's now clear, because current coming into this node, it's not going anywhere else, so it has to leave as well. So this is Ix, so Vs is Ix Rs. So my Ix will be Vx by Rds minus Ix Rs by Rds plus Gm multiplied by 0 minus Vs, that is Ix Rs. So this is taking on the LHS. This is Ix Rs by Rds. This is minus. This will also be plus Ix Gm Rs is equivalent to Vx by Rds. Alright. Ix common 1 plus Rs by Rds plus Gm Rs is equivalent to Vx by Rds. So my Vx by Ix is Rds plus Rs Rds plus Gm Rds Rs. So giving it a good shape, it will be Rds. If I take Rds as a common, will be 1 plus, then I will take Rs as a common, 1 plus R, 1 plus G. No, there is some mistake here. Gm Rds. Sorry, this is Rs. So this will be Gm. One second. So if I just multiply it on this side, this will be Rds times 1 plus Rs by Rds plus GmRs. Okay, so my R out is Rds plus Rs 1 plus Gm Rds. Okay, this is R out. And we need to find R total. So this is R out. So my R So we found the R out, right? You had the same value for R out?
I committed a mistake, sir. It's your
Is it different?
yeah. What I calculated is different, sir. You are all correct.
What was the, can you just spot your mistake and you can do it correctly? Alright.
Yes,
So now what we need to do is, let me just write here only. My R total will be R output parallel to RD, right? So what you need to remember here, this is a standard equation now. Whenever you connect a source resistance, you just need to remember this relation is that it goes like this. This is the intrinsic resistance plus what is your source resistance, and the factor is 1 plus gain, intrinsic gain. Okay, this is intrinsic resistance plus source is plus the factor of the source that adds to it is Rs times 1 plus gain. Okay, this is how it goes, and you can calculate the R total while just because RD can be anything, so I have kept it as R output parallel RD. Just remember this equation. Okay, so this will help your analysis. For example, if you have anything, let's say this is your transistor now. I want you guys to directly give me an answer for this. This is my V in. This is my V out. You know what is gain? Gain is GM times
LCM R out.
GM times R out. Okay. Now, let's say this had a source resistance Rs. Okay. So now you can directly write what is R out looking here and looking here. Total R out will be R1. Let's say this is R2. R1 parallel R2, right? So you can directly write R1 is equivalent to intrinsic resistance plus Rs plus 1 plus gain. Gain is intrinsic gain. RDS. This is your R1, and you can directly write R2 as RDS2, right? This is RDS2. Okay, so you can directly write gain as GM times R1 parallel R2. That comes out to be this equation parallel to this equation. Now if you remember this equation, you can directly answer these type of questions. Okay, so let's see if we can apply this in this part. Okay, now you have 3 transistors here, and we need to worry only about M1, correct? So
Because of input, sir.
okay, yes. So what I can do is I can directly calculate what is the R out looking here, okay, and what is the R out looking here, correct? So can I directly write a resistance here, and I write a resistance here, and this equal to RDS3, and can I write this equation as, sorry, not RDS3, you are not correcting me, so this is 1 by GM3, right, parallel RDS3. So this is like this, and this R out is, you can write it as 1 by GM3 approximately as well, like we had done the approximation for earlier. And this R out is for M2 will be simply RDS2, right? Right? So my gain is GM1 times looking into here. Let's say this is R1, this is R2. So this will be R1 parallel R2. Now can you tell me what is R1? Can you tell me what is
R1
R1?
is RDS2, sir.
Now we just did the analysis earlier right here. What was this analysis for?
Okay, RDS. Okay, sir. RDS. RDS2 1 plus GM1 or RDS2, sir.
RDS2, here your source resistance is RDS2.
Yes, sir.
Okay, so what I told you to remember is this resistance, or I would looking, so can you turn off your mic? Okay, so this is your source resistance, and if you have, if you want to calculate this R out, what you do is This R out is intrinsic resistance of this transistor, that is RDS1, plus source resistance, that is RDS2 here, RDS2, multiply by 1 plus gain, intrinsic gain, that is GM1 multiply by RDS1. This is your R out here, that is your R1. Okay, so my R1 is RDS1 plus RDS2, 1 plus GM1 RDS1. This is 1, and now R2 is, let's assume it as 1 by GM3. Now you can calculate R1 parallel R2, right? And then you can use this relation to calculate gain. So was it easy? If you remember this relation properly, you can solve these type of questions easily. Okay, just do one thing, just do this. I have done this by using this method. Try to make an equivalent circuit. You know how to draw the equivalent circuit. For your reference, I will just draw the equivalent circuit for you guys, and you can solve it at your home. Let me just draw here. So can you tell me what are these? Okay. Yes. Okay. This is okay. We have done one mistake, and you didn't point that out. So this is a PMOS, right?
Yes, sir.
Okay. So this is a PMOS, and it is a diode connected PMOS, right?
Yes, sir.
This is its. This is ground. This is source. This is. Okay, so what will be, we are looking at the source. When you look at the source, what is the resistance? 1 by GM, right? So this should have been 1 by GM. Check that, okay? Because when you look at the source, your resistance comes out to be nearly equivalent to 1 by GM. Correct? Or not?
Sorry, sir. Could you repeat again, sir? I'm not getting.
What, you are not audible?
Yes, sir. Yes, sir.
It's correct, right? So just check that. This is how we will do this question. You just need to use this formula, okay? And let's draw the equivalent circuit for this. We have here. Let's draw first V input. Input here. This is source. This is GM1, VGS, RDS1. Okay. Now you see that drain is connected here to the M3. Let's draw its gate here. Let's draw its source. Source is to be grounded. Current goes from source to drain. That is VSG. This is RDS, and this is connected to V out, and this is also connected to V out. Correct? And we have source here. Drain is grounded here, and This is shorted gates, so gate is also permanent. So that means this will be 0. You only have RDS2. Okay. So you can do the analysis now, right? What you need to find is V output by V input. Do this by two methods. One, which I showed you to calculate the resistance directly, then GM multiply by those R out. And another is you can just directly draw this equivalent circuit. And you will see that this GM here, G is at V out, VG is V out. So there is some value of GM3 VSG. VSG is here, that will be minus times GM V out. Do this analysis and come up with an answer and compare it with this, the method I showed you by calculating the resistance. All right. So, okay, so are there any questions in that?
No, sir. Sorry, fine, sir. Could you please discuss the last question, sir? Question 11, sir. That's it. That's fine.
Question 11.
Okay, within a week, we have some techniques.
Okay.
Question.
Okay. I guess this is more of the same type of question. What is here? You have this R. Okay. Input is given at this terminal. Okay, you have to calculate. One approach will be simply again to equivalent circuit, but that will be, I guess, equivalent circuit. That will be complex. Yeah. Another approach you can do is now you can calculate the resistance here. You calculate the resistance here. This is a drain. You are looking in the drain. You are looking into the drain. That will be R. Let's call it as R2. Your R2 will be simply equivalent to RDS3 plus RDS4. Is it correct? Will it be RDS3 plus RDS4? Yes, because we are looking into the drain. If you look in a drain, that will be simply RDS. Look, no, not directly actually. This will be the source degeneration for the next transistor, right?
Yes, sir. Yes, sir.
So let's just let me just give you the steps. So first find this R4. Our output for 4 will be simply RDS 4, and this RDS 4 will be in series with M3, right? Okay, but this is grounded. Let's check this. GMVGS RDS 3. All right. We need to find the resistance here. This is Vx, Ix. So this will be Vx minus Ix times RDS4 by RDS3. I think yes, it's correct. This is again the source degeneration. You can just directly find it using the previous method. So this will be your RS here, that is RDS4. If you now look here for R3, you know the value now, right? Your R3 will be what will be your R3?
Sir, GM3.
That will be RDS4 multiplied by 1 plus GM3 RDS3 plus, what was the another term? Its own resistance, right? RDS1 plus RDS1, right? So this will be the resistance here. And you have to
RDS4, sir.
RDS4.
RDS3.
Okay. RDS3 is right here.
No,
Okay,
sir.
this is RDS3. Yes, yes. So this will be your total resistance here. R output 4 3 plus R output 4. Okay. Just to cross check, I want you guys to do this. Make the circuit. Okay. This is Vx Ix. Find this resistance and check that if it comes equivalent to this. Okay. Can you do that later on? And you can tell me in the next session. So this is how we will find the total output resistance on this side. Now we need to find the total output resistance from this side. Okay. So if when you have to find the total resistance, what you will do is that you will ground this, right? This will be grounded. Okay. So this will come. Yeah, let me just draw this.
Sir, RDS1, no, sir.
Okay.
We
Thank
use
you, guys.
that
So this
resistance
will
of
be
M1.
simply. This will be a simply like this. Um, this is a transistor here. And this is NMOS, right? This is NMOS. So this is NMOS here. So now what you are doing is this is your V output. Now first you will find resistance at this point. Okay, find a resistance at this point. Find resistance at this point. This will be a resistance R, correct? And it will be in parallel to this resistance. This is the NMOS. That means this is source, this is drain. Now you are looking into the drain. So this will be simply
RDS1 parallel with R, no, sir.
RDS. Yes, correct. Absolutely correct. RDS1. So R output here will be R parallel to RDS1. Okay. So now it will be in series to this. This is a PMOS now. Now this is a R parallel to RDS1. This is a PMOS. Just be careful with it when you are saying that it's a PMOS and because it will change the terminals. Just this is a PMOS. Now this is R. If this is a PMOS, that means we need to
Drain.
okay.
Yeah. Intrinsic gain. Means,
This is source. This is drain. Now if this is the PMOS, you are looking at the drain. You are looking at from the drain. So this will again be the source degeneration. Now for the source degeneration, your R output is
R plus RDS1.
intrinsic. Your intrinsic. What is your intrinsic here? M2
Yes, sir.
RDS2 plus your source resistance, that is R parallel RDS1, right?
1 plus GM2 RDS.
1 plus GM2 intrinsic gain
RDS.
RDS2, correct?
Yes.
So
Yes.
this will be your this resistance. Okay. And one more thing, this please don't add this. Don't add this here. I just said it incorrectly. Uh, you don't need to add this because we have used it as a source degeneration. So it will be total of R out here. This will be your total R out looking on this side. Okay. So this is your total R out here. And on this side, total R out is this one. And let me just notice R out up, R out down. Okay. Now you know the gain. Gain will be
GM1 minus GM1.
no. Okay, we did one mistake here. We did one mistake here. Okay, this is a just only calculate this value. This one. This is the R out down, right? R
Yes,
out
sir.
down is okay. R out down is okay. You calculated this value.
Means
Then
R out down. First M4 will find out R
yeah,
like
yeah,
yes.
yeah.
So for
First
again
find
put
out.
the source
First find out
regenerator, sir.
M4. Then this will be a source regeneration for M3. Find the
Yes, sir.
total resistance. This will be V out. Then after that, I will suggest using the equivalent circuit because you have to take the V output from this node. Okay, we did it. No, we did wrong, and this analysis is not right. So please instead. Then after this, once you find the source resistance, then it becomes an easy question. You just need to draw an equivalent circuit. Okay, and this is like this. This will be simple like this. Okay, this is again grounded. So you can just make the equivalent circuit and then find the V output by V input. Try this. If you are not able to do it, then we can do this in next session. We can start with this one. Any other question apart from this one?
Nothing, sir. Fine, sir.
Okay, just try it at home, and if you are not able to do, we can do this in next session. Just
Yes,
you just understood the steps, and now I think you should be able to do this.
yes, sir. Sure, sir. I will try and I will ask you if I.
Okay, okay. Okay, so I think we can end up the session. If you don't have anything to say, so we can close the session now. If you have any confusion, please don't hesitate to mention in the next session. Try this, try to remember the formula and try to solve the questions of this line. Okay, so see you guys next week.
Sure, sir. Thank you, sir. Thank you so much, sir. Very
Okay,
informative.
bye bye.
Thank
Sir,
you.
sir,
Bye bye.
that method what you said, no, sir. The GM into R out. You follow the reservoir, no, sir.
Yeah, yeah.
Yes.
Okay. Try to solve the questions as much as from the Razavi, you will get a good intuition and good hold on solving these type of questions. Razavi is a very good book for analog.
Yes, sir. Thank you,
Okay.
sir. Thank you so much.
Okay. Okay. Bye bye,
Thank you.
guys.
Bye.